Good morning, Ben. Hope you're doing well. So far we've talked about how to find derivatives, but we really haven't talked about how to use them. And today we're going to use them for graphing. The technique I like to use is called sign charts. It has a lot of names, but it's not usually taught in your standard calculus classes, but I found it to be really, really useful. And the easiest way to go through it would probably just be to kind of go through an example and show you what a sign chart is and what kind of information you can glean from it. I should look that up. Look it up. Okay. So we're given this equation and we're asked to find everything about it. And by everything, we're like, well, maximum, minimums, roots, concavity, etc., etc., etc. And we'll probably be asked, like an actual question, what's a maximum, etc., etc., of this point of this graph? What is the maximum, either absolute or relative? So first thing we do is we start by drawing up our sign chart. So a sign chart would look something kind of like this. Start with a line, whoop, whoop, or it's a sign chart. It will start with a line. Whoop, type, ooh, a little bit. There we go. I like that, authoritative. There we go. Maybe a little bit bigger, a little bit bigger. Okay. So we have our line, first part of our table, and we'll say we have up here X. And I'll draw little axes up here for our graph. I'll do it like this. There we go. Good enough. And so we have, nope, I don't like it, I know. I should just settle. Call it good enough. Cut my losses. Not happening. There we go. There's one axis. And whoop, there's the y-axis. Something like this. I'm more happy with that. There we go. Whoop, whoop. So we have an x and we have a y. And so we start by writing out x. We'll say f of x below it. We'll then do f prime of x down here. And then at some point we may look at f double prime of x. But the idea here is first we want to look at, when you think of a graph, what are the important things to think of? Well, you think of, all right, what are the roots? What would solve this equation right here? And this goes back to algebra. So to solve this, we would probably look at this and be like, all right, let's we'll factor out an x. So this would be x times 3x squared minus 4x plus 1. And we'll copy and paste this guy, bring it down for some more real estate. And we're like, okay, so at this point, we have y equals, we know y can x can equal 0. X equals 0 is a possible solution. And then anything that solves for this would also be a solution. And this then would be the quadratic equation. Quadratic equation, negative b plus or minus b squared minus 4ac square rooted all over 2a. This gives us, let's see, b is 4, so negative 4 is 4 plus or minus b squared, which is 16, minus 4 times 3 times 1 square rooted all over 2 times 3, which is 6. We'll say 6. Okay, and we're left with 4 plus or minus square root of 16 minus 12, which is 4, all over 6. So we have 4 plus or minus 2 over 6, which is 4, nope. So it will be 4 minus 2 is over 6 is 1/3, because you have 2 6, which is 1/3, or x also equals 6 over 6, which is 1. So we have 0, 1/3, and 1. Those are solutions. So what that tells us then, come back up here to the graph, we have 0 I'm going to write this as 0.33. We don't have to be exact here. And the amount of exactness you need will depend on the problem. We're just trying to here to graph it and try and get an idea of what this graph looks like. So 0.33, close enough to 1/3. So those are, we know, will be the y-intercepts. And so we draw that up on our sign chart. So we do have I probably should put a 0 up here. So we have a 0, probably about here, 0.33. I'll move up the bottom of the y-axis slightly just to get out of my way. And then we have a 1 over here. And we know that each of those goes down to results for f of x as 0. Because that's how we found them. That was the whole idea. Okay, from here then we're like, all right, so let's find some maximums and minimums. So this is where we go to what's called critical points. Critical points, there's a lot of definitions for critical points. The one that I'm going to use is critical points are where the derivative equals 0 or doesn't exist. And so that gives you that gives you the possible maximum and minimums. You'll see what I mean in a sec. So basically it's saying you have a graph, looks kind of like this, then that would be a critical point, that would be a critical point, that would be a critical point, because the derivatives all equal 0. But then also if you have something kind of like this, so it comes up pointy, and then goes to some sort of, I don't know, asymptote, you're like, well, derivative doesn't exist here, also critical point. Pointy, which means not derivative, the derivative does not exist, therefore that would also be a critical point. Something that I also like to count in as critical points. They're not really critical points, but you kind of have to think of them anyway in life. What are the endpoints? So you have a graph here, I'd call the endpoint there and that point there critical points. The critical points tell you local maximum and minimum, basically meaning that this point right here is higher than its two neighbors over here. I know you get infinitely close in and it's kind of hard to tell, but if you zoom in, eventually you'll see that, all right, that is the highest point. When you take the limit approaches that point in the middle, it's the highest. That's the idea of a relative or local max or min, is that it's higher than its neighbors. An endpoint, it might be higher than one of its neighbors, but it might only have one neighbor. That's the idea here. So you might have what's called an absolute max or min, where, okay, that's a bad example, but if something goes up like this, it's like, okay, that's an absolute maximum, because we're looking at the graph, it's like, well, if it had a neighbor to the right, it would probably be bigger. But it doesn't have a neighbor to the right, so it's probably only, so compared to the neighbor on its left, it's the biggest, and it's bigger than everything else. So that'd be the absolute biggest. Absolute maximum just means the highest overall. So an local max or min can also be the absolute max or min, but not guaranteed. When we talk about absolute, you have to look at the endpoint as well. So to recap my criteria that I established, critical points, terrible. So the derivative, I'll say f prime of x equals 0, or does not exist. And then you should also keep in mind the endpoints as well, because those are also possible absolute max or mins. Critical points will just give you relative max or mins. So to find where the derivative equals 0, we first should probably find the derivative, which seems reasonable. Clear that guy out, go to that guy, kapow. So we have, write this guy up here. Maybe I can just do it like this. Haha, I bet you I can. So, ooh, green. So, f prime of x equals 9x squared minus 8x plus 1. Because we just did the power rule. Bring the 3 down. Yep, bring the 2 down. Yep, and then you can say there's kind of a 1 here. You bring that down, you get x to the 0. X to the 0 is 1. We are left with 1. Okay, so then this is the derivative of y with respect to x, or f prime of x. So what we want to do now is we want to solve this for the roots of this equation, and that'll give us our critical points. So we do this, I was like, darn. Okay, so again, we're just going to go, we're just going to go straight to the quadratic equation. So negative b plus or minus b squared minus 4ac square rooted all over 2a equals, and if you guys don't know, this is the quadratic equation, you should know the quadratic equation. So 8 plus or minus b squared, which is 64, minus 4 times 9 times 1 square rooted all over 2 times a, which is 18. 2 times 9 is 18. We then have 8 plus or minus, let's say we have 64 minus 36. 5, carry the 1, 14, is that an 8? 14 minus 6, yeah, I think that's 8. 28 plus or minus 28 square rooted all over 18. We'll factor out a 4. So we'll have 2 times 4 plus or minus square root of 4 times the square root of 7 all over 2 times 9. Do the canceling. Cancel, cancel, cancel. 2 is the same thing as square root of 4. And we're left with 4 plus or minus square root of 7 over 9. Okay. We're not going for exactness here, so we will get the calculator. Let's see here. Calculator. On. Clear. Move down slightly. 4 plus second square root of 7 divided by 9. And we have 0.74. 0.74. Or, go back to our calculator. Come back, calculator. Can I just go up here and do a... No. There we go. 4 minus second square root of 7 divided by 9. We have 0.15. So we have 2 more points here. So we're going to put those on our sign chart. Whoop. Ooh, this is the dark. Green it is. Okay. So we have 0.15, 0.74 comes down, and we know that f prime of these numbers, f prime of 0.15 and f prime of 0.74, give or take a bit, is 0. Because that's what we solved for here. That was the idea of the quadratic equation. We found the roots of the derivative here. And so, boom, boom, boom. Yes. Very nice. So now, what we want to do is, so we know that if we put these on our graph, we have our 0.15 and we have our 0.74. I don't know why I put it. I'll put a 0 here just so it looks consistent. We know that we have either a max or a minimum. And we could plug in 0.15 into this equation and find out what the actual value was. We don't care that much yet. We might though. We should. That's a good point. We should. Okay, so we will do that. Get our calculator. Calculator. Clear. So we do, is it 0.15? 0.15. I know, I should be more exact. I'm not. Minus 4 times 0.15 squared plus 0.15. Okay. And we got 0.07. Okay. 0.07. 0.07. Okay. And we'll do the same thing but with 0.74. So 0.74 to the third. Let's do 3 times on this side. 3 times. Ah, no. Should then insert. That's okay. 0.74 to the third minus 4 times 0.74 squared plus 0.74. Reasonable, and it's even the same length. We have minus 0.23. Oh, check real quick just to make sure I didn't mess it up. Yep, good enough. Okay, so it's probably going to be where this is the maximum and that's the minimum. But let's take another slightly deeper look here. So we have our derivative here, and this gives us our slope. So what we're going to do then is we're going to take the equation for our derivative, move it over there. Whoop, wow, that's a lot of work over here. Well, it's going to go away. Hop, hop, gone. So we have our derivative, and what we're going to do then is we're going to plug in points on either side of our maximum and minimum, because this will tell us our slope, either up or down, so to speak. So if we plug in, we'll choose a point that's convenient for us for calculational purposes. So for here, we want to choose one here, one in the middle, and then one on the right. So I'm going to start by doing f prime of 0, because 0 is easy to calculate. So we have 9 times 0 minus 8, also times 0, plus 1, which gives us 0 minus 0 plus 1, which is greater than 0, therefore increasing. So we have, what I do then is I draw an arrow like this on my sign chart. Then we'll do 0.33, but I'm going to round that off to 1/3, which actually was the original value anyway, so that rounding actually makes it more exact. So we have 9 times 1/3 squared is 1/9 minus 8/3 plus 1. So this becomes 1. So 9 over 9 is 1. So we have 2 minus, I'm going to call this minus 8/3. 8/3 is, so 6/3 would be 2. So 8/3 is greater than 2. Therefore 2 minus 8/3 is less than 0. Therefore the derivative will be negative, therefore it's going down. And so what I do here then is I'll draw this down. Okay, now we're going to pick another point to the far right. I'm going to use 1 just because it is convenient to use 1, because we're just looking for a greater than or less than 0. So I could choose anything greater than 0.74. I could choose 0.75. It'd just be a huge pain to calculate. And we could do it with our calculator, but I like to avoid using the calculator if I can. Every time you use a calculator, you just add one more chance for a human performance error. And so I like to avoid it when possible. 9 times 1 minus 8 times 1 plus 1 equals 9 minus 8 plus 1. 9 minus 8 is 1. You add 1, that's 2, which is greater than, equals 2, which is greater than 0, therefore increasing. And so we have increasing here. Okay, so at this point we can draw a pretty good picture of our graph. And depending on what you're looking for, you don't really need the whole sign chart. And you can see, wow, this took a while to do. It can if you go all the way through it. You can go through it quicker if you're not jibber jabbering like I am, but you're just focused on doing the problem. So we'll start by looking at, so now we can look at our max and mins. We can see here that it goes up until it gets to 0.15 and then starts going down. So when you go up and then start going down, that's going to be a maximum. And you can see similarly for 0.74, you go down and then you start going up. When you go down and start going up, it's like you've hit a minimum. Think of this as hills and you're running over the hills. You have your peaks and valleys. There's actually more formal name for this. This is called the first derivative test because you're using the first derivative, which is f prime of x, to determine maximums and minimums. So when we draw this up, we'll draw something like this. So we'll do, all right, 0.15. This gives us the value of, so 0.07. So you could also do it like this, 0.07. Draw it on this side. Delete. This will not be drawn to scale. So we know that it starts at 0, goes up to 0.17, reaches a maximum, comes back down to 0.33, and then reaches a minimum at 0.74, and then it comes back up to 1, and then it keeps going up forever. So I'll draw an arrow. So our graph, though not drawn to scale, probably should do something more like this, because this goes down to negative 0.23. Negative 0.23. So this is drawn much higher than it needs to be. Get rid of the 0.15. I'll just move it up. So to draw it slightly more to scale, we have something kind of like this. So it comes up, goes down, and then we get a, we can do better with that one. There we go. We'll draw in the maximum first, and then there we go, kind of like that. So we have our maximums, we have our minimum, and we have our roots. And this is kind of a picture of what the graph is going to look like. So let's verify this real quick with Wolfram. Hop, hop. Y equals 3x cubed minus 4x squared. So 3x cubed minus 4x squared plus x. 3x cubed? Yeah, seems reasonable. Click. And we have something like, yep, that's kind of like what we drew from 0 to onward. A little bit of hump here. We have a maximum, we have a minimum, and then comes up. Bum, bum, bum. Yeah, looks like we did pretty well. There's a little bit more we can do too. So we don't have to stop with the first derivative. We can do the second derivative as well. So I'll copy the bar. And so the first derivative, that gives you slope, up and down. The second derivative, f double prime of x, that gives you concavity. The way I like to think of concavity is the ability to hold water or not. So if you think of it like this, you have a bowl like this and a bowl like that. Concavity would be the ability for when rain comes down like this fills up with water. That would be positive concavity. If you have negative concavity like this, water comes down, it's going to run off the side and not hold water. So in a layman's way of saying it, if it can hold water, positive concavity. If it doesn't hold water, negative concavity. And that's the easiest way for me to visualize what's going on here. And so I erased the derivative, didn't I? For shame. Okay. So we have f prime of x equals 9x squared minus 8x plus 1. Therefore, f double prime of x equals 18x minus 8. And we find the roots for the second derivative of x. And before, we called those the critical points, basically where the derivative equals 0. Now, where the second derivative equals 0, these will be called inflection points. You might have heard the term inflection points before when you're doing chemistry, specifically with regards to titrations. You find the I think the equal point. There's a term there. I should look it up. So we just set this equal to 0, and you move negative 8 over, you get 8x equals 8. X equals 8 over 18. Divide both by 2, and you have 4/9. 1/9 is about 0.11. So 4 of those would be about 0.44. So between 0.33 and 0.74, we'll have 0.44. And I'm going to represent this by a tilde. I think a tilde. Right about there. So what happens there is if you take this part and you dump water, this part would fill up with water. But if you removed this and looked at this side, water would come down and fall off the edge. So at this point, this right here at 0.44, that's where you have this inflection point change in concavity. We're going to draw this up here too. We'll do it right about here. Come down, have a 0 here. And we can look at this and be like, okay, it's probably negative on the left side, probably positive on the right side. But we're going to test it anyway, just to be sure. So we'll put in our points probably 0 and 1, and we'll use those because they're the easiest to calculate. So f double prime of 0 equals, wait a sec, let's figure this out. 18 times 0 minus 8 is negative 8, which is less than 0, therefore negative concavity. F double prime of 1 equals 18 times 1 minus 8, which equals 10, which is greater than 0, therefore positive concavity. Okay, and the way I do this is basically the frowny face, happy face. So I draw it like this. This is a sign chart. This is pretty much not the most complicated, but you probably won't do many sign charts that are more involved than this. I know this took us like half an hour to do. So you're like, oh, how can I solve a 15-minute AP exam free response question using a sign chart when it takes me 30 minutes and I only have 15 minutes to do it? I understand. Very legitimate concern. You do have to be pretty quick. And you don't have to do the whole thing. We did pretty much the whole thing here to answer everything. You, most of the time, don't have to. So one of the key points here with concavity is it will tell you also max and mins. This is actually referred to as the second derivative test. You have first derivative test, second derivative test. And so the way you think of this is, all right, so we have a maximum or minimum because we have a critical point, the point where the first derivative equals 0, basically right here. This tells you max or min. And if we have a max and min and the concavity is down, then you think of it basically looks like a hill, top of the hill will be a maximum. So it's like, yep, that's totally true. We have a maximum right there. That's called the second derivative test. I wouldn't worry too much about memorizing the name. It's kind of good to know, but it's more the concept. It's not that hard to memorize. You're like, oh, second derivative test gives me the answer. Okay, so then here we have the bottom of the hill, and then we have a max or min. Therefore, it's going to be min. And so I probably should have lined up the smiley face with this right over here. There we go. That would probably be a better way of lining it up. And using the concavity like that can help you draw your graph a little bit better. And depending on how much information you're given, you might have to use it or might not. So that's the idea with the second derivative test. And the thought process here is, okay, so how would this appear on an AP exam? What kind of question would be asked? How would I address it? So the question that would be asked might be something along the lines of, so in the interval from, let's say, 0 to 0.9, it'd probably be something like this, from 0 to 0.9, what is the maximum value of the equation 3x cubed minus 4x squared plus x? Then justify your answer. So the way you would address this then would be, okay, you make your sign chart, you find the roots, and you find the maximum and minimums, and then you look at the endpoints. So if it was from 0 to 0.9, then you would find, all right, this endpoint, that endpoint, the maximum and the minimum, because you'd find the minimum based on critical points, and then you test them to find out basically which one was the biggest. And what the justify the point is like, well, how would you know that this is the maximum. Now the AP exam doesn't look at sign charts as the actual justification, because what you do in reality is you make up your sign chart. You do your 0, 0.33, 1. I guess it would be 0.9 in this case because that'd be your endpoint. And you'd look at 0.15 and 0.74 and be like, okay, you draw your arrows like such, and you're like, all right, this is my maximum because the slope comes up, comes down. This is the endpoint. But the problem is, how do I justify that on the AP exam? And the AP exam doesn't view sign charts as justifications in and of themselves. They're like, here's the sign chart. And I can understand their point here. The idea, it pretty much is the justification, but the AP exam really isn't concerned with the justification as much as you demonstrating knowledge. And it's the sort of thing where you can do sign charts just through rote memorization following the algorithm without any actual knowledge of what's going on in life. And so the way you would justify it would be based on the first derivative test, the slope to the left of 0.15 is negative, the slope on the right of 0.15, or slope on the left of 0.15 is positive, slope to the right of 0.15 is negative, therefore, based on the first derivative test, x equals 0.15 is the maximum. And then you could also say the endpoints were tested and were less than the local maximum. And that would be the justification. So when you're asked to justify, you can use your sign chart, but you basically just read off what your sign chart says. Goes up, comes down. Between the up and down was a maximum using the first derivative test. Or if you don't have access to the first derivative for whatever reason, or you just want to use the second derivative test, because sometimes it's easier to take the second derivative, be like, based on the second derivative test with a negative concavity, the critical point, 0.15, is a maximum. Or if you're looking for a minimum, based on the second derivative test, the point at x equals 0.74 is a minimum. And that's how you would justify your answer. And this is how you would basically go around justifying your maximums or minimums. This is how also you would graph your equations. So a quick side tangent. Whoop, I'm going to erase everything. Erase everything. I know, it feels like we did so much work and it's gone. Whoop, click. Talk about the mean value theorem. This is kind of like an extra something. Not something. So, the mean value theorem. We're going on a slight tangent here. What a jeu de mots. Okay. So you have some equation like this, a function, a graph. It looks like this. And the mean value theorem goes that if you take the slope from the beginning to the end, kind of like this, then what it says is, we'll say this is point A, this is A, this is B. So you take the slope from A to B, and it says that if it is continuous, basically you draw without picking your pen up, and it's differentiable, basically means no pointies, and it's not pointy anywhere basically, then you will be able to find somewhere on this graph I was stuck to it. Something like this. Oh, here we go. You are a there we go. Yeah, I'll say that's about right. So it says that somewhere on this graph there will be a slope with that value. So the idea is you have your average slope, mean slope, and then there will be at least one point where that slope exists on your graph. So here it'd be like, right about there, or maybe right about there. That's all the mean value theorem is. I want to touch on that because there's not really another good place to touch on that in the course. And so when you hear the mean value theorem, that's all it says. That's all it means. No need to panic. Excellent. So now let's take a look at an example problem, something you can find on the AP exam. So this is an AP exam question from, I think, 2016, one of the free response questions. So you have about 15 minutes to answer all these parts, which is, that's a lot to do, not a lot of time. So we're going to do just the first couple parts because that's all we've really learned how to solve so far. So we're given, consider a differential equation, dy dx. It's a differential equation because it involves a derivative, dy dx, which is a derivative, equals x squared minus 1/2 y. This kind of looks like what we'd see with our implicit differentiation techniques that we looked at. Find d squared y minus dx squared in terms of x and y. Okay, so what this is saying is, I'm going to redraw that out real quick. It's saying find the second derivative. So if this would be the same as f prime of x, and this would be the same as f double prime of x. And it's kind of funny the way they do their notation. So what this is really kind of, what I like to think of this as, is when they do the d squared dx squared thing, it's kind of like d squared dx squared of y, which is kind of saying take the derivative with respect to x of y, and then take the derivative again with respect to x. And that's why you have the squared on the x and you have the squared on the d. And that's kind of why that notation looks like that. So try not to get too caught up in the notation. One of the more challenging parts about the AP exam, and this question, in particular, is just trying to figure out what they're trying to say. So the actual problem itself, not too bad. Finding out what they're asking, that's a little bit more challenging. Okay, so now that I've wasted, 2 or 3 minutes of the 4 I get per portion. Okay, focus. So we have, I'm going to write this as f prime of x, just for clarity, equals x squared minus 1/2 y. And so the second derivative would be f double prime of x, which would be, and this is the same thing as our implicit differentiation. I'll write 2x by the power rule times derivative of the interior, which would be dx over dx. What I took was the derivative of the x in the middle, minus 1/2 y. So this is kind of like y to the first. So it goes down to times 1 y to the 0. All right, like that. Times derivative of y with respect to x, because we're taking the derivative with respect to x. And then I would simplify this. So dx, that's just 1. Pretty much whenever you have a one value over the exact same value, pretty much always going to be 1. We can ignore the 1 here. Y to the 0, well, that'll also be 1. And we are left with 2x minus 1/2 dy dx. Whoop. Now, what it asked us in the problem was in terms of x and y, which specifically in this case means not dy dx. But, huzzah, we know what dy dx is. dy dx is up here. dy dx is the same as f prime of x, which is this value right here. I'll get rid of that 1 there just for clarity. So what we have then is this equals 2x minus 1/2 times x squared minus 1/2 y. We just plugged it in. So distributing things, 2x minus x squared over 2 plus y over 4. And this would be our answer to part A. Make sure that's a 2. Okay? And find d squared, second derivative of y with respect to x. Check. Done. Go team. Now, let y equal f of x. Okay, that's kind of sort of what we've been doing. Be the particular solution to the given differential equation whose graph passes through point -2, 8. Okay, so when you see particular solution here, you're thinking, what does that mean? So it just means that if we plug in -2, 8 into this equation, it'll work. It won't break, it'll make sense. We won't get something like 3 equals 8. For example, if we said like, I don't know, y equals 2, or 1, 2, whatever, we plug it in, the numbers break, it gives us something crazy. that would not be the particular solution. When they say a particular solution here, it means we can plug these values into this equation, this differential equation up here, and it works. They're like, oh, okay, that works. Okay, that's fine. I'll believe it. Does the graph f(x) have a relative minimum, maximum, or neither at the point -2, 8? Okay. So, first thing we should do is, so we have, I'm going to draw up our sign chart now. So we have x, f of x, f prime of x. Clean up the real estate a little bit. Hoop. And we have, so we have f double prime of x equals this. And then from here then, I probably should have a f double prime of x over here as well. And we'll draw some lines to flesh out our sign chart. And we know that the x points we're dealing with here is -2. And we know that -2, when we plug that in, it gives us 8, because that's the x value, that's the y value. And f of x is basically y. So we can take a dy dx here, plug in -2 and 8, and find out what the value is for f prime of x. So we have -2 squared minus 1/2 times 8. 1/2 8, yep. This gives us 4, which equals 0. Makes sense. So we have a critical point at -2, 8, which makes sense because now it can be a maximum, minimum, or possibly neither. So then we need to find out, okay, does this have maximum, minimum, or not? And we have, what we do then is we have our second derivative, f double prime of x. So we'll take our f double prime of x, we do f double prime of -2 equals -2 times 2, yep, minus -2 squared over 2 plus 8 over 4. What we did was we plugged in -2 and 8 for our second derivative. And in all fairness here, I put f double prime of x, but this should probably actually be f double prime of x and y. So when we solve this, we have -4 minus, this is +4 divided by 2 plus 2, and we're left with 4 minus 2 plus 2, which gives us -4, which is less than 0. Therefore, we have negative concavity. And so when we go over to our sign chart over here, we have, I would draw something kind of like this. So you have a negative concavity. So when they ask us, all right, is this the minimum, maximum, or neither? We're like, okay, so we have -2, 8, which is a critical point, a potential min or max. It then has, then did the second derivative test, and we got a negative concavity. So I draw negative concavity, kind of like at the top of the hill then. And so point -2, 8 is a maximum by the second derivative test. And if you have time, I'd say, because by second derivative test, having a negative concavity at x equals -2. So you basically say negative concavity, x equals 2. That tells us that we have a maximum. And that's how we would address this problem. And that's kind of how we'd use a sign table with this. So to backtrack what we did here, we were given some points. We looked through the points. We found a second derivative. We then plugged these into a table. We showed that -2 was actually a critical point because the derivative came out to be 0. We then took that critical point and we looked at the second derivative, which was negative, and so we knew that that critical point then was a maximum. And our justification is, well, by the second derivative test, and we said that the concavity was negative at that point, which shows that it would be a maximum. And that's how you would justify it. That's the justification. You can't just be like, well, look at my sine table, it's obvious. Well, you look at your sine table and it is obvious, but you want to be able to demonstrate a little bit more knowledge in that. So that's the idea of how you do graph equations, concavity, slope, and we also covered the mean value theorem briefly. And that's the idea of how you approach these problems. Hope it helped. Next time we'll go over some other concepts like L'Hopital's rule and dealing with limits that are a little bit more challenging.